Swayam Prabha. Digital India. Educated India.
So this course is about stochastic process in chemical engineering, but the development of stochastic process in chemical engineering came much later, but the genesis of this field originated in physics and mathematics. Okay, so I want to give some small discussion on the historical perspective of the stochastic process and see how this whole field came about. Now, we are all very familiar with the deterministic approach of modeling a process, and when we do that, we already discussed that there are conservation laws, there are constitutive relations, we have certain variables that we are interested in, there are some control variables, we want to see how a control variable affects the observables and so on. So, when we look at all this, we see that the variable of interest varies very smoothly in time. Okay, that's one of the very characteristic of a deterministic model. But what happens is that in reality, even those quantities have inherent fluctuations, and what we see as a continuous description of the system is only an average behavior. Okay, so I can qualify this statement with some example. Let's take a very simple piston cylinder arrangement that we see in thermodynamics. So we have an ideal gas which is in equilibrium with the external pressure. Okay, so imagine that you have a piston cylinder assembly. Okay, some gas is filled in here, ideal gas. Now suppose this is an equilibrium system, so the pressure is balanced, thermal temperature is balanced, and so on. So now let's say that these is molecular species, so they are constantly moving, and they will keep on heating this piston surface here. And now let's say you measure the force acting on the piston. Okay, and then you plot the pressure, instantaneous force as a function of time. Okay, so this is so we measure the force because of the incessant collision of these molecules. Okay, this piston surface will experience a force, and you plot the force as a function of time. What would you expect the behavior of this property? How would the force change with respect to time? Just tell me whatever you feel like. That's okay. There's nothing like a right or wrong answer. What do you expect intuitively? Okay, there will be an average, and then there will be some fluctuations. Okay, so first we will talk about the fluctuation. So if your instrument is sensitive enough with which you are measuring this force, you are likely to see some sort of a fluctuating character as a function of time. But you see that it kind of reaches some sort of a plateau value about which it is fluctuating. Okay, so I said already that the system is in equilibrium, it is not changing from one state to the other state, there is no dynamics inherent, but the variable itself has some sort of a fluctuating character about a mean. So if I take a time average, okay, so a running time average would show as if like a force is constant in time. Okay, so this is what you would have expected. You would have expected the force should be constant like this. Okay, but in reality it's going to be this kind of fluctuations. We generally ignore that fluctuation. We say that the force is constant like this. Okay, so let's say that whether we this approach or this approach, whatever it is, we see that this force per unit area times volume follows some sort of a law. Okay, so this pressure versus pressure divided by area, the force divided by area is pressure, and pressure times the volume of the gas will be equal to RT, because we know this is ideal gas law. Okay, so what we are saying is that naturally any variable that we look at it have a fluctuation, but then if I look at the time average of this property, that will follow a nice deterministic relationship. Okay, this statement can be made about any other deterministic equations that you know of. Okay, all systems will show some fluctuations. The question is, they are not too big, the fluctuations are not too big, okay, and you are okay with the average behavior. Okay, so then this force that I have here, I should say this is a time averaged force. Okay, and we say that's time average force I think F bar, yeah, F bar. Okay, so when you time average a signal, you get this force, and I call this as a time averaged force. This time averaged force by area is what we call as a pressure, and then we say this is a thermodynamic variable. Okay, and we say first law follows, second law follows, constitutive relations follows, and so on. Okay, this is one example, and another example is if you have a particle suspended in a liquid, and then you are looking at the center of mass of this particle as a function of time. Okay, when you see that, you will see this kind of a character. Okay, I am plotting x coordinate or y coordinate as a function of time of a Brownian particle suspended in a liquid, and if you look at the trajectory, you look at the x component, y component, you will see that it kind of goes about it, and then here also you will see the mean position or the mean x coordinate or y coordinate will be 0. Okay, so that's, we will come back to this particular problem later on, but the point is, just like the force was fluctuating, here the coordinates of a Brownian particle also fluctuates. So this dynamics looks very irregular, as much as it was irregular here. Just like how I can do a time average here, I can also do a time average here, and you will see that if I do a time average, and you will see it is 0. And I can go on to say another example. If you look at the current in a circuit typically, and if you measure the current, that will also have a fluctuating character. But then if you take the square and mean it, take an average, I mean time, if you do a time average of the square, if you do I square like this would have a finite value and well behaved value, and then you can see that the power in the circuit can be nicely expressed as I square R. Okay, so we know all these Ohm's law and electric circuit theory, in which we use not just I square but mean of the I square. Okay, and that will follow a nice relationship. So far we were only familiar with these kind of deterministic equations. Okay, but now what we are saying is, those deterministic variables that we have been using so far are nothing but the mean characteristics or the average properties of underlying fluctuations. Okay, and that can be force here by a pressure, or it can be a Brownian particle position like here, or it can be a current in a circuit. So these are some of the initial observations that was made about the fluctuations, inherent fluctuations, and how we should take care of the time averages. Now, in terms of the mathematical treatment of stochastic process, everything started from the intention of explaining Brownian motion. Okay, so that was the beginning, and from there onwards, I think the applications become very broad. So what I want to do now is I want to kind of show you the fundamental work done by Robert Brown in 1800s about the observation of Brownian motion, I'm going to show some small summary. So the paper was published in 1828. And I have just taken the summary from his paper. So what it says is that he conducts this very long experiment, and then finally he concludes this. Okay, I'll read it for you. It says this: extremely minute particles of solid matter, whether obtained from organic or inorganic substances, when suspended in pure water or in some other aqueous liquids, exhibit motions for which I am unable to account, and which from their irregularity and seeming independence resemble in a remarkable degree the less rapid motions of some of the simplest animolecules of infusion. Anyone can guess what is this animolecules of infusion means? What he was referring there is nothing but microorganisms. Okay. So in those times, this bacteria, virus, those terminologies are not very much used, and people were looking at biology, molecular biology. They were studying microorganisms, and in that particular contemporary literature, animolecules of infusion basically nothing but microorganisms. So here he is saying that when solid matter or solid particle, when they are very tiny in size, whether they are derived from organic matter or whether they are inorganic matter like oxides, other solid particles, whichever way it is, when it is suspended in pure water or in any other aqueous media, he sees that this irregular and they exhibit irregular motion, and he is not able to explain why that motion happens. Okay, so that's where he kind of completes this study, and he says that these dynamics the motion looks very similar to how a microorganism would behave in a living system, even though he says these particles are not living. He is saying it's inorganic solids from organic or inorganic materials. Okay, so he knows that these particles are not living materials, just like the microorganisms are. But yet he says, why would they move? We know that why bacteria move and how we know the mechanics of how bacteria move and all that. But these solid particles have no such inherent living mechanisms. So why would they move or how would they move? That was not clear. Then he says that the smallest moving particles observed, and which I have termed active molecules, so he called them as an active molecule because they look like a very different class, appear to be spherical or nearly so, to be between 1 in 20,000th or 1 in 30,000th of an inch. He is talking about a micron size. Okay, if you take 1 inch and divide by 20,000 or 30,000, you are talking about roughly about a micrometer. And that other particles of considerably greater and various size, either of similar or very different figure, also present analogous motions in like circumstances. Actually, if you have time, you should read this paper, because for an experimentalist, this is very inspiring, because as an experimentalist, he goes on to investigate as much as possible. He takes rocks, he takes ashes, he goes to volcano, takes some volcano particles. I mean, whatever he can make particle out of this 1 micrometer range, he has made. Okay, organic, inorganic, living, non-living, etc., etc. Okay, so very beautiful experiment. It's a very long paper, 30-40 page paper. He just goes on and on about what are the things he has observed and nicely noting it. Okay, so very interesting paper. So this was the beginning of the Brownian motion and interest, and later on, even though this happened in 1828, the theoretical development actually happened during Einstein's times. So I can point out 3 important developments in order to explain this irregular motion. So Einstein's theory was published in 1905, and Stochastic (1906), and Paul Langevin in 1908. So these are the initial developments, mathematical developments of this theory. So Einstein's theory was first put forth, and he pretty much characterized all the observed exhibits, and Stochastic independently developed more of a mathematical character of the problem rather than the physical characteristics of the problem. And later on, Paul Langevin, he also rediscover whatever Einstein and Smolchowski predicted, but then with a much simpler mathematical treatment, okay, to describe the Brownian motion. So now what I will do is, so we will discuss some of these aspects of Brownian motion from a very simple to a little bit more sophisticated treatment, and then we will take it from there. Before we discuss the treatment of Langevin and Einstein's approach, we will take a very simplest, the most simplest approach that you can teach a high school student about Brownian motion. Okay. So again, when we think about Brownian motion, we have this picture following with what Brown was saying, that there is some particle of micron size suspended in water or water-like liquid. This could be of any origin, organic, inorganic, nearly spherical, not necessarily spherical, etc. All these characteristics are nicely summarized here. So that's the picture that you should have in your mind. And then we are interested in finding out some statistical aspects of this motion, which he says the motion is very irregular, and I have not seen something like this. I think he is probably comparing the motion of planets and other celestial body where it follows a very regular dynamics, okay, whereas this one doesn't show such a regular dynamics, so they look very chaotic and irregular. Okay, so that's what he's saying. I'm not able to account for this motion, so I don't know what it is. So he calls this active molecules. So now what we will do is we will try to set up a very simple one-dimensional random walk approach, and then see what comes out of this analysis, and then whether this can explain what we have shown here as a Brownian motion. Okay, so that's the context. So we are thinking about one-dimensional problem. So we have a one-dimensional axis here. I will discretize the space 0. I think I have a, yeah, I say this step size is delta, okay, some length dimension like delta. This is 2 delta, and then goes to infinity. And in this case, I have minus delta, minus 2 delta, and then goes to infinity. Okay, so this is the axis that we are going to say. This is what we mean by one-dimensional random walk. Okay, the space is one-dimensional. Now, initially, what we will do is we inject n particles here. We say n identical particles. So the initial condition is that we inject some n number of identical particles at the origin. Okay, so then this particle will now move. Let's give some rules for the motion. Okay, we say that the particles can take a jump from one lattice point to the other lattice point. Okay, and that length is delta. And then we also say that we'll bring the time later. Let's just imagine that you have an account of how many steps a particle has jumped. Okay, that would be like n, small n, and we see that the particles jump a step length of delta. Okay, I am giving a rule for the motion. I am saying that each particle can only take at a given time take a jump of delta. They can't go 2 delta, they cannot take half delta steps. I am specifying the step jump to be delta. Now next is about the direction, whether it's going to be only going forward or whether it's going to be going only backward. Here we say another rule. We say that the particle can choose either direction at equal probability. Okay, so particles can go forward or backward at equal probability. So here we have only two options. So when you say equal probability, I mean 0.5 to the left and 0.5 to the right. That's a probability. We also will say that the particles are not interacting. Particles do not interact. So it doesn't matter how many particles are present here for another particle to decide to come here or to leave from here. Okay, so they don't really interact. Imagine like they're ideal. Also, this probability is independent of where the position is. Okay, so when I have a particle at the origin, it can go 50% times this way or 50% of time this way. The same probability holds if the particle were to be here also. So this probability rule is independent of the current location. Okay, so these are all the rules. Okay, let's again go over one more time. What we are saying is we are restricting the problem to one dimension, and the space is now discretized into a unit step length of delta, and I am starting with origin, putting n particles of similar kind, identical kind, and the particles are allowed to move backward or forward with a probability of 0.5 each, and this probability is independent of the current location, and the particles do not interact. Okay, these are set of assumptions that we can make. So with this, what we can ask, what is given a particle I, what would be the current location? Okay, so that's something that we can ask, and then we can deduct some information, useful information from there. Xi is the ith particle's position after n jumps. Okay, so this can be now written as some sort of a recursive relation. The current position is nothing but the previous position. What should I have here? Probability of, or the actual distance it has covered, that would be plus or minus delta, isn't it? So I am asking after n jump where the particle was, I look at the previous position, that would be xi n minus 1. From here it would have gone to this side or that side. Okay, and this delta is a step length, as I said before, because the jump only adds same distance of interval at every steps. So for example, you can say that xi1 would be xi0 plus or minus delta. So this is initial position, which is origin. Once, if you look at the particle after the first jump, it could have either be at the plus delta or it could be at the minus delta. This statement is for the first statement, first step. When you extend this to n step, this is what you can write: the previous step plus or minus delta. Then we can ask, what is the mean position of the n particle after n jump? Okay, so I am going to use this symbol x of n, and this would be average of all the particles n, sum over xi n. Correct? I said I have n particle, each particle is individually undergoing this random walk problem, and I am saying that what is the mean position of all this n particle after nth step. Okay, please don't confuse between this n and this n. This capital N means the total number of particles, this n is the number of jumps it has made. It's more like a time here. I will replace this n as a time subsequently. Okay, just imagine this like a time variable. So now I have already given a recursive relation to this from here, so I can write xi n minus 1 plus or minus delta. So what will happen here is when you sum over with all n, and since each steps are going back and forth equally likely, you will see approximately half a particle would have taken the positive step and half a particle would have taken negative step. So when you average over n, this term will become 0. Okay, and what survives is only this term, and this is nothing but the mean of x at n minus 1. So what we are saying is the mean position after n step is nothing but the mean position in the previous step. Okay, that means from one jump to the other jump, the mean has not really changed, right? And what would be this equal to? N minus 2, mean at n minus 2. And if I extend this, I will be able to show this is nothing but the mean position of the initial state, which is nothing but 0, because that is where I introduced the particle here. So as far as the mean character is concerned, the particle position is 0, mean position is 0. That is an important result of the Brownian motion in one dimension. So even though, now we ask, is it enough to say that the mean position of the random walk or the Brownian motion is 0? Is that all that we can say? If we say that, if you stop here, it would mean that as if the mean position is changing, so as if the particles are not really moving effectively, but that is not the case, right? We see that the trajectory is evolving, only the mean position is 0. So we should not stop here, we should look at other moments, higher order moments, other behavior outside the mean. Okay, so we can ask, what is the mean square position? Okay, mean is 0, but what about mean square position? The same way when I look at the current fluctuation, I looked at the mean square, right? Similarly here we can ask, what is the mean square position of this particle? Okay, and we see that whether that's going to survive or that also going to vanish. So what we want is, we want this x square and the mean of this. So here I have taken only the mean of x. So here I am taking the mean of x squared. And I will expand this bracket. Here what happens is that when I expand this expression here, so the first term is nothing but the mean square at n minus 1, and the second term you will get as just delta square, and because of this plus minus term, when you sum this will become 0. Okay, this term will vanish. So then what we are saying is, unlike the mean behavior, mean square behavior is different. So here for every one jump, the mean square displacement is increasing by a unit of delta square. So the mean square at n is the mean square at the previous time step plus delta square. Okay, and if I write this recursively, I can show the mean square distance after n jump is n times delta square. Okay, and this is a non-vanishing quantity. Okay, if you increase n, and this n is when you increase n, the mean square displacement also proportionally changes. Okay. So now what we will do is we will just replace this n in terms of time. So t here is the time, and we say tau is the time required for one jump. So the total time divided by time taken for one jump will give you the total number of jumps. Okay, so we can replace that here. Now n is replaced in terms of time. Mean square displacement as a function of time is or you can say delta square by tau is t. So from here, if you calculate the root mean square displacement by taking square root of this, you will see that this gives in the dimensions of length. This is in the dimension of length squared. Okay, when you take the square root, it gives in a kind of how much distance you have traveled at an average. I mean, not an average, but this is a root mean square displacement, and that goes as a square root of t. Okay. Now, if you want to compare this with the Newtonian mechanics, you would have predicted x of t would be x naught plus some v t. Okay, if you have a particle moving at some velocity v, you will see this distance is proportional to t. But the Brownian character has a different dependence on time. It goes much slower. It goes square root of t. Okay, so you can see this mechanics is quite different from what we know from classical mechanics. Okay, so this diffusive motion is what we call here. The random walk motion or the Brownian motion or the diffusive motion is far slower compared to a kinematics like this. Okay, so we are basically introducing a new kind of dynamics here. The Brownian particle follows a different dynamical rule. So this is where they say, right? I mean, if you have a cup of coffee, you put some sugar, and if you let it, the sugar molecule to diffuse and become uniform, it's going to take a very long time. By the time the coffee would have become cold. That's why you need to stir. When you put stirring, you are inducing convection. You are actually not believing only on the diffusion alone, but you are looking at some sort of convective transport to speed up the process. So diffusion by nature is very slow, okay, because of this time dependence. Now I quickly here give the main results of Einstein's treatment of the Brownian motion, and then we will compare what we have predicted from the random walk in a simple treatment and what was obtained from Einstein's treatment. So BM means Brownian motion. So what he derived was the probability of finding a Brownian particle at position x at time t. Okay, and he showed that this would be So what Einstein derived was the probability of finding a particle at place x at a position x and t, and he showed that this is basically a normal random variable, okay, or a Gaussian distribution, okay, and this Gaussian distribution has a characteristic of mean 0 and the variance or the mean square as 2 dt, okay, where d here is the diffusion coefficient. And this is defined as kBt by 6 pi mu r. So kb here is the Boltzmann constant, T is temperature, mu here is the medium viscosity, and r is the diameter radius of the particle. So these are all dependent on the condition and the particle characteristics, okay, that determines the diffusion coefficient, and this diffusion coefficient is what dictates how the diffusive behavior is going to be, okay. So as a chemical engineer, you all know about diffusion coefficient from Fick's law, right, and you can see the molecular origin of diffusivity comes from this random walk behavior or the Brownian motion of the molecules, right. So and then if you compare this and this is a normal random normal distribution, and then comparing this and this, you can see mean and standard deviations are given by this. And now if you come to this, we did predict in this case one dimensional random walk that the mean is 0, and the mean square displacement we predicted this to be proportional to t, and that was this is also, right, and then if you match the prefactor, what we have assumed here as delta square by tau is actually nothing but 2d. In this treatment, we did not take into account of the properties of the particle or the medium viscosity or temperature. We did not say anything. We said one physical quantity delta which will determine the step size, another physical quantity that says how much time it will take to jump. These are some arbitrarily fixed quantities. We did not associate any physical character to this, but this derivation did account all the physical aspects of the solvent as well as the particle, because of which he was able to show that the diffusion coefficient which factors in the mean square displacement could be related to the physical aspects of the solvent, temperature, and the particle size, okay. Now by matching this result with this, what we have assumed as unknowns delta and tau is actually nothing but related to diffusion coefficient, and the dimension wise also it's consistent. This will be some meter square by time, and this is also meter square by time, okay. So you can see that this is more detailed work. I didn't show the derivation, but this one is very, very easy to comprehend and understand, okay. The more important thing is that we understand the mechanics of this problem, not necessarily look at the details, okay. But we also see the analogy between what is done by Einstein's problem here, more a sophisticated approach, versus very simple one dimensional approach. You start with a very basic rule of random walk, you can arrive at the same result, right. And of course, if you want to plot this function, you will see that at time t, this will be a delta function, and then as a function of time, you will see that it would spread. It's supposed to be symmetric. Okay, this is what is going to happen. Okay. In terms of an experiment, this would basically mean if I have a very quiescent room, I inject a small amount of drug, a dye or perfume, and then see how this molecule diffuse in space, you would actually see this kind of a prediction. Okay. Over time, it kind of diffuses out, but the mean position is still where you injected. Okay. Mean position is still 0, but to the extent it actually traversing the space will be going to proportional to this square root of t. Okay. So from a transport phenomena point of view, diffusion is not very good because that's very slow. Chemical engineering is all about process enhancement and process intensification. So you want to make process faster, the kinetics has to be faster, and you can see diffusion alone you cannot deal with. Okay, diffusion is a very slow process. But from a biological point of view, diffusion is all the mechanism that microorganisms have to explore, forage for food and exploration. Okay. So I hope you appreciate this new thing that we understand here, that the dynamics of a Brownian motion is very slow, and where is it coming from, and in what scenario this exists. These are all very important. Okay, that size is very important. Micron scale is very important. Okay, and in that in that length scale, Brownian diffusion is the dominant mechanism. Yeah. Why Einstein consider? He didn't consider. He derived this. What I showed is the final result. There is I skipped several. So he basically sets the rules like here. Okay, let me give you some background. So what he did was he just tried to hypothesize what the molecules of the solvent is doing to the particle. Okay, so he imagined that these molecules are bombarding this particle incessantly, and there's a large number of molecules colliding at the same time, and that is very irregular. And then he predicted what would be the statistical characteristic of that force. Okay, so he said that maybe the mean force is 0, but then the mean square force is not 0, and he put that detail, and then he derived this this function. Okay, I will be talking about in the next class on Langevin dynamics, in which I will bring this characters of the force that is acting on the particle. With that, we can probably understand how this Einstein derivation was done. Okay, so now what we can do, what we have done is one-dimensional random walk, and we predicted all this. Now we can extend this to 2 dimension and 3 dimensions. Because that is more realistic from a practical point of view. So when you look at 2D or 3D, you can actually make the same kind of statement. For example, you can say this is the x component. Similarly, you can write for the y component also. The one component I assumed need not be x. I could have done the same thing with the y and z, and I would have got exactly the same results. Okay. Now, when I look at the 2-dimensional random walk like that, so I have to write the mean square displacement r as x square of t plus y square of t in 2 dimensions. In 3D, this would be like this. Each dimensionality adds 2 dt of mean square displacement. So in 2 dimensions, the mean square displacement will be 4 dt, and in the 3 dimension, it's going to be 6 dt. Okay. So similarly, here I have written for 1 dimension. If you do for 2 dimension and 3 dimension, you will also this 4 dt and 6 dt. Okay. But in all these cases, the coefficient d is fixed by these factors. Okay. If you want to increase the diffusivity, you have to increase the temperature, or decrease the viscosity, or decrease the particle. Okay. You see that the diffusion coefficient is only affected by these 3 variables, nothing else, right? Whether you have a metal particle or an oxide particle, or you have a polymeric particle, doesn't matter. The chemical makeup of the particle does not factor here, only the size does. Of course, we have assumed shape to be spherical, because I have written a drag force for a spherical particle. If I had a non-spherical particle, this expression would change. Okay, for a spherical shape, only parameter is the radius, right? Okay, so we'll kind of wrap up here.